Artificial intelligence has been witnessing a monumental growth in bridging the gap between capabilities of humans and machines. Researchers and enthusiasts alike, they work on numerous aspects of the field to make amazing things happen. One of many such areas is the domain of computer vision. The agenda for this field is to enable machines to view the world as humans do, perceive it in a similar manner, and even use the knowledge for a multitude of tasks such as image and video recognition, image analysis and classification, media recreation, recommendation systems, natural language processing, etc. etc. The advancements in computer vision with deep learning have been constructed and perfected with time, primarily over one particular algorithm, that is a convolutional neural network. A convolutional neural network CNN is a deep learning algorithm that can take in an input image, assign importance, that is learnable weights and biases, to various aspects objects in the image, and be able to differentiate one from another. The pre-processing required in a CNN is much lower as compared to other classification algorithms. While in primitive methods, filters are hand engineered, with enough training, CNNs have the ability to learn these filters and characteristics. The architecture of ConvNet is analogous to that of connectivity pattern of neurons in the human brain and was inspired by the organization of visual cortex. Individual neurons respond to stimuli only in a restricted region of the visual field known as receptive field. A collection of such fields overlap to cover the entire visual area. So this is how you work with the image data. So essentially an image is just a form or is just a matrix or array of numbers or pixels. So first you get this 3 cross 3 pixel image, and then we flatten it to a 9 cross 1 layer. So all these 9 pixels are flattened and arranged in this particular manner. So this is how you work with images in Python or deep learning. Next, as you can see, an image is nothing but the matrix of pixel values, right? So why not just flatten the image like a 3 by 3 image matrix to a 9 cross 1 vector, as you uh, looked in the previous slide, and feed it to a multi-level perceptron for classification purposes? Not really. Multi-level perceptron is basically an artificial neural network. So what you have studied, like in the ANN, you have your input layer where you can feed all these 9 cross 1 vector as the input. But in case of extremely basic binary images, the method might show an average precision score while performing prediction of classes, but would have little to no accuracy when it comes to actual complex images having pixel dependencies throughout. So ConvNet is able to successfully capture the spatial and temporal dependencies in an image through the application of relevant filters. The architecture performs a better fitting to the image dataset due to reduction in the number of parameters involved and reusability of weights. In other words, the network can be trained to understand the sophistication of the image better. So this is your normal image data, a 3 by 3 pixels, and since this is a RGB image, so we are having three color channels: red, green and blue. The height is 4 pixels and width is 4 pixels. So this is your typical image data that you will work with. You will get to understand this data better when we move to the practical example and how we implement a CNN using TensorFlow and Keras. So you will see this image data in the form of a NumPy array. Now you can imagine how computationally intensive things would get once the images reach dimensions of say 8K, like 7680 cross 4320. The role of ConvNet is to reduce the images into a form that is easier to process without losing the features that are critical for getting a good prediction. This is important when we are to design an architecture that is not only good at learning features but also scalable to massively large data sets. So this is how a convolutional operation works. So let's consider 1 2 3 4 5 6 1 2 3 4 5 6. So 6 cross 6 image input. So all these are the pixel dimensions. 6 cross 6 your input image. Now you have this separate image patch that is taken out of this entire image, and you have a kernel filter, and when you perform the convolutional operation, So this first value is multiplied with this is multiplied with this, the third one is multiplied with this. All these values are multiplied and then we are adding them to get the output. And finally, this input image is reduced to a 4x4 image after performing the convolution operation with this kernel. So this is your basic convolution operation. Here, as you can see, this is the kernel 101010101. So finally, if you multiply this, this becomes 0, this is 0, this is 0, this is 0, and you add up all the remaining ones. So 1, 1, 1 and 1. So this 4 is essentially the result of multiplication and is placed over here. If you take this patch, this 3x3 section, the answer will be 3 and it is placed over here. Similarly, for this 3x3 patch, this answer will be 2 and it is placed over here. This is a convolute feature after performing convolution operation with the input image and the kernel filter that we are using. The next thing that we'll do the pooling. So this is a filter of 2x2 and this is a convolute image feature of your 6x6 image, which is now reduced to 4x4. Now what we have done, also there is this new term called stride. So stride is basically the distance that you move. So if I take, let's say, this 2x2 section, and if I choose the value of stride equal to 1, then the next 2x2 section will be this one. I'll show you one more time. Let's say this is my initial 2x2 section, and if I choose the value of stride is equal to 1, then this will be my next 2x2 input section. But if I choose the value of stride equal to 2, so it will skip 2 boxes. So this will be my first 2x2 section and this will be my next 2x2 section. Similarly over here, if this is my first, then this will be my second. So this is the meaning of stride, the number of boxes or the cells that we want to skip to perform the next operation. This was about stride. Now let's understand about pooling. If I perform max pooling on this 2x2 section, then the maximum value will be pooled to create a new feature or the reduced feature that will extract the maximum information from this one. Similarly, 7 will be extracted from here, 6 from this 2x2 and 8 from this 2x2. So here, after performing max pooling, we are getting this reduced feature. Let me show you one more example. So this is max pooling and this is your average pooling. So there are different pooling techniques that you can use, but mostly we use max pooling for better results. In average pooling, what it will do, it will add all these and it will divide it by 4, and this number, which comes out to be 13, is placed over here. Similarly, 30 plus 2, that is 32, and 32 divided by 4, it comes out 8 and 8 is placed over here. This is for average pooling, but if you do max pooling on this, then 30 is the maximum value from this 2x2 section, so it is placed over here. So these are all pre-processing steps of your convolutional neural network. All the practical implementation of this you will see in the video where we practically implement CNN using TensorFlow and Keras. So this is the entire life cycle or pipeline that we follow. This is your input image of 28 cross 28, so 28 height, 28 width, and since this is a black and white image, so we are having 1 over here. And then we perform convolutional operation with 5 cross 5 valid padding. Then we again do max pooling, again a convolution operation, and again a max pooling. So this 28 cross 28 cross 1 is now reduced to 4 cross 4, and then once we have flattened it, and this is your normal fully connected ANN artificial neural network. Over here we can predict the different classes in the output layer. So once all these convolution steps that are performing the convolution operation with the kernel and performing the pooling, this is done, and then finally we have a normal artificial neural network or a fully connected neural network that we saw in ANN. So this is the full life cycle or the pipeline that we follow for a typical CNN project. So I hope you are clear with all the concepts that are discussed in the video for CNN. Thank you for watching the video. Now let's move to the next one.